Thank you again for coming. So, what I would like to discuss today is how to capitalize what we have seen, the mathematical machineries that we have seen so far, and some other related things. So, this is lecture 4. So let me recap quickly what we have seen so far throughout this week. So we started with this motivation that deep neural networks somehow are capable of learning about these things and then be able to perform different data that have been seen during the training period. And it seems that there's connection between how flat or sharp the local minima that you reach while training are. And in particular, the flat one seems to work better on this unseen data than sharp ones. And an interesting phenomena that has been observed is depending on heavy tail, the tail distribution of the stochastic gradient noise, the global behavior of SPD can be quite different. And also this small variant of SPD also leads to qualitatively different behavior. So this was based on so in the second lecture we looked into the detailed mathematical machineries for characterizing the catastrophe principle and conspiracy principle. So again, conspiracy principle was the light-tailed variant dynamics. In other words, system-wide rare events arises as if the whole system has conspired out to drive you toward a rare event. The heavy-tailed environment leads to conspiracy principle, catastrophe principle, where everything looks normal, but there are just a few small number of components that behaves catastrophically different, so that system-wide rare event arises. So this was on the first example, the insurance example, where we are interested in the large loss over a long time period. And we have seen some catastrophe. So the first example was the law of large numbers, so nominal behavior. So regardless of heavy or light tail claims you have, the nominal behavior more or less same because of the law of large numbers, which only require first moment being finite. On the other hand, the rare events can be drastically different depending on whether the tails are heavy or light. And this was the illustration here. So the 10 conditional distributions start to show very different behavior depending on whether the tails are heavy or light. So in the light tail case, again, it's conspiracy in the sense that it's not. The behavior is just tilted from the nominal behavior, but the overall shape is still flat, straight line. In the heavy tail case, almost everywhere things look just normal. So a straight line with upward trend, but there's just one single catastrophe. And depending on the rare event, these patterns may actually change, and so that if you have, for example, constraint on the size of the jumps, then actually the number of jumps it changes to 2 from 1. So the catastrophe can arise from two big jumps. Okay, so this was catastrophe principle and conspiracy principle, and the large deviation formulation, very useful for characterizing this, was in this form. And of course, this roughly means this. And J of A was the important quantity. That was the number of jumps that you have to add to the nominal scenario. And because the large deviation formulation here is exact asymptotics rather than log asymptotics, we actually get the conditional convergence. So the conditional distribution of the stochastic process converges to some random object, which can be precisely identified. And that random object is piecewise constant function. So basically the nominal function with added jumps. And we have seen some examples of these manifesting. And we are going to get back to some of these examples later, but it can be a pretty complicated example like this. And by the way, this is digression, but this, so what's the, how to compute the smallest number of, or what's the smallest combination of upward and downward jumps in this example? So that, it's not very obvious that it can be easily computed. But it turns out that if you have continuous upper and lower bounds, then there's a greedy algorithm actually to compute this. So, but this is just digression. But the point here I'd like to make is on the left-hand side, to identify the most likely scenario, you have to solve some variational problem. On the right-hand side, you have to solve some combinatorial problem. So you decide the location of the jumps and size of the jumps. So this becomes combinatorial problem, and it's not you don't always have efficient solver for this, but in this particular case, for example, you do. So yeah, this is, there might be some new class of optimization problems that optimizers may want to pay attention. Okay, so, and then more complicated examples can be also dealt with, this catastrophe and catastrophe principle in particular. And the reason was because it's sample cat version of large deviations. So the large deviation formulation is with respect to the path, in the path space. And the key tool was the M convergence, and I was not super clear about what was which part of this was whose contribution. So the way the M convergence was formulated the way it is by Linsco, Rhee, and Resnick, and then the continuous mapping theorem was also Linsco, Rhee, and Resnick. The slight variation, so almost continuous mapping theorem was ours, but that's just small, subtle, small variation. And the asymptotic equivalence and the way you obtain the M convergence for in the product space. So you have two random objects with two M convergence. You can combine them and consider in product space. But that product, like the naive product, doesn't give you the right answer. You actually get a loser bound. So you also need to strengthen the M convergence by combining multiple M convergences. So those were from our first paper. And then we also mentioned that the new heavy-tailed large deviation formulation was the right one in the sense that the classical one actually fails to be established as within J1 topology. All right. So now moving on to the third lecture, we have seen the generalization of the heavy-tailed large deviations. So what we have seen in the second lecture was large deviation for the processes with independent increments, so random walks or Levy processes. But it can be generalized to more general dynamical systems, and stochastic gradient descent of one example, but we focused on this. So what we have seen was that stochastic gradient descent, as we scale the learning rate, converges to a deterministic process. So gradient descent, gradient flow. So we have seen that the nominal path or a law of large numbers limit was the solution of OD, and there were many of them. And then we have also seen the manifestation of that law of large numbers, and just as in the simpler independent increment processes, there's no difference between heavy and light cases. But when it comes to the rare event, again, heavy-tailed large deviation formulation allows you to characterize the rare events precisely. So again, the important quantity J was the number of jumps that you have to add to the nominal path, so gradient flows. And adding gradient jumps to the gradient flow means just following the ODE at almost everywhere, except for you just add jumps at a few given time points. And obviously, what the asymptotic upper and lower bounds roughly means is that the rare event becomes rare as the scaling parameter increases at this rate. Particularly, this is polynomial rate, and the rate is decided by J of A. And so we have seen that because of this, we depending on whether it is clip or not, the number of jumps required may be one or multiple. And in unclipped case, it was the catastrophic principle, the large deviations manifest the way that we have expected. Again, almost everywhere it follows the gradient flow, but there's a single big jump that drives you out of the current alternative. And then, so the truncated version has the same law of large numbers limit, and but J of A changes depending on the ratio between the radius and the size of the clipping threshold. All right. So, and you can also confirm the manifestation of this with simulation results. So here you see more closely that almost everywhere it follows the gradient flow. In other words, the SGD heads toward the local minimum. So if it's on this side of the local minimum, then it goes down. If it's on the other side, then it goes up. So it does follow gradient flow almost everywhere, but there are just two extreme perturbations that drive you out of the current attraction field. All right, so from there, we have seen my goal in the last lecture was to provide some accessible introduction of the machinery required to establish this result and understand these results. And the point here was the large deviations, the heavy-tailed large deviations formulation that was based on the M convergence. It's actually not exactly enough for the global dynamics. And what we actually need was the uniform version of it. And it's not like we don't actually need like globally uniform. All we need is actually just locally uniform. In other words, as you consider small neighborhood of the starting point, you want these types of bounds. And so the right tool for that turned out to be a uniform version of M convergence. So Xingyu has came up with this uniform M convergence framework and has proved the portmanteau theorem for uniform M convergence. And then once you have the uniform version of M convergence or uniform version of heavy-tailed large deviations, asymptotic atom is the condition that allows you to elevate the heavy-tailed large deviations to local stability analysis. So just let me take 1 minute to appreciate the relationship between equations. So the large deviation, if you look at this, the large deviation analysis, the probability that you escape from a local basin, whether it's clipped or not, it is a rare event. So it's unlikely to happen. But this is over a finite time horizon. So if you only wait 1 of t over eta times, then it's going to be less and less likely to be able to escape. So t over eta is still a longer and longer time horizon, but it still becomes less and less likely. But if you wait even longer, so no matter how rare it is, if there is a stochasticity, rare event will happen even if you wait long enough time. If you let a monkey to randomly type, then eventually the monkey will write a Hamlet. So that's going to be astronomically long time, but it will happen. Mathematically, in the limit, it will happen. So the same thing here, SGD is going to linger around local minimum, but from time to time, it's going to deviate from a local minimum. Because, the point where the stationary distribution of accumulates. But the first question is, how long do you have to wait? So the asymptotic atom allows you to combine this knowledge about finite time horizon, or let's say a linear time horizon, to this infinite horizon, and decide how long it takes to escape from this location. So one major result was that if you have asymptotic atom, then you have this exit time and location analysis. A very precise, very sharp limit, asymptotic limit for the exit time and exit location. And this asymptotic atom is precisely, it characterizes precisely which conditions you need to check to have these types of results. Okay, so from here we were able to get this convergence of exit time. So especially in particular, we were able to identify the rate, the scaling parameter with which the exit time converges to the exponential distribution. And from there, we were able to establish sample path convergence. In other words, the sample path of the scaled SGD converges to the sample path of the continuous time discrete space Markov jump process. And in particular, these Markov jump processes have a state space consisting only of flat local minima, y-disk local minima. So anything that's not the y-disk disappear from its trajectory. So these pictures can all be precisely explained by these machineries that we have seen. All right, so now the first topic that I'd like to discuss today is how to capitalize these machineries to in actual training of deep neural networks. So I briefly explained this toward the end of the first lecture, but let me quickly remind. So you have stochastic gradient typically comes from having small batch. You have now you have seen from Umut's lecture that how precisely write these things down. But so you get a small batch stochastic gradient by considering only subset of the data, computing the loss of the subset of the associated with the subset of the data. And what we do here is to inflate the stochastic gradient by adding mean zero noise multiplied by heavy-tailed random variable. So I think there were some confusion after the associated with my first lecture. So I didn't make it very clear there. I think that the heavy tails, at least in the exogenous form, doesn't seem to be present in the typical deep learning, or at least the benchmark image classification tests. So if you think about it, it's pretty clear because you have finite number of data. So and the randomness comes from sampling, like subsampling from that. So in precise sense, you cannot have infinite support. The stochastic gradient noise should be something that's supported in a bounded space. However, of course, that doesn't mean that it's not it's irrelevant to heavy tails. Even if it's so remember the reinsurance example. So there, the same phenomena exactly same phenomena will happen even if you consider you replace the heavy tails with the truncated heavy tails. As far as the truncation threshold, the threshold that you truncate the heavy tails is larger than the reinsurance threshold. So it doesn't. So this heavy tail formulation is not really about whether it is indeed heavy tail in the infinity. It still manifests as far as you have some tail that's reasonably close to heavy tails. And I think Diana has done some work related to this, like when the heavy tail phenomena appears and so forth, like up to which point. But the point here is that you don't really need true heavy tails to see heavy tail phenomena, but in deep neural network, that doesn't even seem to be the case. So everything, at least exogenous noise, seem to be light tail. So what we have done is to inject heavy tails to actually take advantage of of our own understanding of the heavy tail dynamics. So that's why we inject the heavy tails, and then so because we believe that this is light tail, it's safe to multiply by some heavy tails. Because if this was so we have pretty good control of what kind of heavy tail we're going to get after this. So typically, you would like to add quite heavy parallel random variables. Let's say somewhere between so it may have first moment, but may not have second moment. So you do need first moment, because if you don't, then it's not going to be, the SGD is not going to converge. So SGD will be more like random one. But if you have if you have too many moments, then the tail will be too light, so that you wouldn't see these heavy tail phenomena within the realistic training time horizon. So we found somewhere around like 2, probably less than 2, most useful. And this was the result that I explained. But let me quickly repeat. So these are our results, and we have 2 because we have 2 different versions where you can either use identical copies of this or independent copies of this. But then the behavior is more or less the same, and what we want to compare is the small batch SGD, which is supposed to perform well. And as expected, large batch doesn't perform as good as small batch, but now these are the variants of our method. So our method involves both injection of the heavy tails and truncation. So this one is truncation only. This one is injection only, and none of these work well. And in particular, the ones with injected heavy tails without truncation. So if you don't regulate the heavy tails, then it actually degrades the performance seriously. And one thing that also is important is that we have constructed mean zero random variable using actual stochastic gradient descent instead of the stochastic gradient noise, instead of the some arbitrary isotropic random variable. So if you actually add just normal standard normal, multidimensional standard normal, it's a possibility conceptually, but it actually doesn't work. You don't get any benefit, and in fact, So
okay, so you have this whole discussion that gradient large bat minus small bat is light-tailed, but in your case you don't look at very high dimensions, right? Or you see it also in the data.
What do you mean?
Well, you said it's justified to multiply this with a Pareto random variable R, and you can control the tail. So you're kind of implying that R has a heavier tail than the other term in the product.
Right. So yes. So that's what. So we believe that these are mostly like.
But like, did you see that if you can, like, if you run the algorithm test problems, you get data from these test problems, so you will be able to do some statistical validation. Did you do that?
Whether they're heavy-tailed or light-tailed.
Yeah.
Yeah, we did. So that's why we tried to confirm the heavy tails from the actual data, but we couldn't.
Okay.
And that, as far as I know, that's other people that's consistent with other people's experience. So
Okay.
there doesn't seem to be exogenous heavy tails, but I'm gonna get back to
There doesn't seem to be endogenous heavy tails.
there. So that's one thing that Umut has mentioned at some point in his first lecture. Like he was not very like he was a little bit vague about it, but so I don't. I guess it's not perfectly clear whether that's true or not, but he showed the multiplicative dynamics.
Right, but that suggests that there is endogenous heavy tails.
Oh yeah, right. So
Yeah, maybe we need a discussion this afternoon after the last talk. Like the two of you fight. A discussion, an academic
So
discussion.
that's actually consistent with my view. So what I'm saying is there doesn't seem to be exogenous one, but if there are heavy tails, then it's probably that.
Oh, okay.
I have another question. So I understand you take the difference of the gradient so that you have the right direction. And you decided to multiply with the Pareto, but you clip anyway. So my question is, couldn't you have taken the direction, normalize, so you remove the magnitude of the gradient, and then just multiply with a reasonable variable?
Right.
So that the magnitude remains the same, less constant size, even if you're decreasing the learning rate, so that you still jump every now and then, but you don't have heavy tails necessarily. So you still see jumps in the limit, but they're not necessarily heavy tails. Isn't that doing more or less the same
that's
job?
exactly like basically multiplying by heavy tails and then truncating. You're actually coming up with a light tail distribution that
Still jumps.
yeah that is associated with the heavy tail dynamics. So this is in the end it's light tail distribution indeed. Like we are running at finite scaling parameter, but they are so it doesn't have to do with the light-tailed limit, light-tailed density, because basically you're not there yet. On the other hand, heavy tail dynamics kicks in already, and it has it provide good enough approximation of actual dynamics. So that's how I view it. So this is so heavy tail does appear here. But in the end, what we do is come up with a light tail perturbation that that provides the dynamics that we want.
Yes, it makes sense.
So there are lots of things that you can think of. So this is just one most straightforward implementation of let's say so yeah, this is the simplest idea that we can come up with from our understanding of the heavy tail dynamics. But you can, for example, instead of using both large and small batch, you can use both small batches or yeah. So there are also you don't have to add heavy tails every time. You can also add heavy tails from time to time. So there are lots of variations that you can think of. We didn't explore enough of those. But what we are showing here is that more or less a proof of concept. So it's not fully optimized results. In other words, Xingyu actually didn't have to tune the parameters much. So what are the parameters? So for example, we have to choose the clipping threshold, right? So that depending on the choice of the clipping threshold, if it's too small, then it's going to be basically light tail dynamics. And in other words, if this number becomes, let's say, 100, then polynomial with 100th power is not much different from exponential tail. So practically you're not going to see it. So the performance is very similar to light tail. And if the clipping size is really big, then basically you're not clicking. So it degrades massively. So there are these two extremes, both bad, and there's a sweet spot in between. And it seems to be pretty sizable. The window seems to be pretty sizable. Yeah, right.
This is for a fixed alpha. And so if you lower alpha, can you clip more aggressively? Because then it will take longer before you reach this high polynomial.
So the choice of we did not try to like explore too many different choices of alphas. We just picked something between 1 and 2, and but if it's too close to 1, for example, so it's in the limit, it's still going to be SGD, but it's going to be pretty close to random. Right? So in other words, it's going to be it's going to try to jump too much too often, so that the convergence will be very, very slow. So it's not really good to pick. So there's obvious lower bound, which is 1, but even choosing it too close to 1 is probably not a good idea. Of course, if it's too large, then again it's becoming close to light tail dynamics. So there should be some right choice, but we don't know.
Like there was this talk at NeurIPS of Charles Martin. He claimed that having a power law index of 2, I don't know if it is 1 in your lingo, or like some people subtract the 1, others don't, right? But like he was claiming that was the best. Yes, like they even have like this website Weight Watcher that you can. It's not for losing weight, but it's for checking the weights in your neural network. If they have a power law that is going to 0 at the right rate, and he kind of came up with this beautiful story that 2 is the magic number. I mean, but it's like.
So yeah, that might be true. I actually don't know, but that's not about the stochastic gradient noise. That's right. It's
Probably.
Yes.
Yeah, I don't
So
like.
wait.
I don't. Maybe need to look into those papers. Maybe even more next week.
Yeah, but then I mean 2 is very plausible number. I think 2 will work well. But I think what we have chosen was more like 1.7 or something, right?
Yeah, I think it's either 1.4 or 1.5. So
Yes.
size is smaller than.
It's 1.4.
Slides was 1.4. Yeah, 1.4, yes.
Okay, thanks.
Okay, yeah, so there are lots of things that we don't know and lots of things to explore, but the point that I'd like to make here is that we were surprised that it worked almost at the first try. Like when Xingyu wanted to try this, I was a little bit skeptical. Like maybe, I mean, why not? But probably we need to understand these things more. Like what's the optimal choice of alpha and all of these things. But somehow there's pretty sizable window for all of these parameters, and some reasonable choice just worked right away. All right. So any other question? All right. So now let's move on to related topics. So now, so Umut mentioned the multiplicative dynamics as a potential reason why endogenous heavy tail might arise. And so I'd like to mention some machineries that is useful for dealing with those kind of scenarios. Here, it's not exactly the SPV with So those multiplicative dynamics that Umut mentioned arises when you have, for example, quadratic loss function, and here it's not exactly that the same setup, but then here, this is also about the multiplicative dynamics, and there's some I think the machineries here can be also useful for those situations. So here the goal is to have again sample path large deviation for random walk, but here it's not IID random walk. So the increments are not IID; they are actually correlated, and they're actually multiplicative. So here nothing is exogenous heavy tails. We don't have any exogenous heavy tails. Light tail, and everything is no building block is heavy tail in itself. But it's well known that if A, so as far as A is log of A is expectation that's less than 1, this is stable, but from time to time it's gonna blow up and then go back, come back, and this blow up will be heavy tail. So of course, if B is heavy tail, then that's going to be the dominating heavy tail. But here we are assuming that it's not, or at least it's not as heavy as A. But you can just make it very light tail. So it turns out that we do get the same form of heavy tail large deviations here, and again, the rate is decided by alpha here, because the this is basically the So this alpha decides the Powell, the tail distribution, the tail index of the cycle, large cycles, and of course this means something like this. But the I need to be clear about the statement of this large deviations. So what's missing here is the topology, right? So all the other large deviation, heavy tail large deviation that I've shown so far are with respect to J1. Here, J1 is not possible because it's not about J1, because the way the heavy tails arise here is because there's this multiplicative dynamics that makes these jumps grow quickly over a short time period. So what this means is that there will be multiple jumps that is going to be merging together. So J1 topology doesn't allow merging multiple jumps. But M1 topology allows merging those jumps. So in this case, M1 is the right choice. And here we actually use slight variation of M1, we call M1 prime, which allows jumps at the very beginning of the time horizon, at time 0.
At the very end.
Yeah.
At the very end, right?
So all right, so the same conditional limit theorem holds. So the catastrophe principle is expected. But let me also mention that another thing that we needed was, again, a little bit of more development in M1 theory, M1 convergence theory, M1 space theory. But so let me explain the reason. So the way you can get this is by considering the regeneration cycle. So the process is going to be, let's say, close to 0, and when it's reasonably close to 0, you can declare regeneration. So in this case, there have been 3 regenerations. So you can aggregate all the jumps in these regeneration cycles and call x1 prime, x2 prime, x3 prime. And then there will be some remainders. So if you consider these, they're going to be basically IID. So you're going back to the IID random walk. But here the problem is that this NT, the number of regeneration cycles, it's not fixed number, and it's not independent of x1, x2, x3. Because suppose that x1 was really big, then the regeneration number of regeneration will be small. So there are correlations. So you cannot directly use the large deviations for the independent measurement process. But still, what we can do is on average, this number will be this big. And if we can establish some sort of equivalence, so hopefully asymptotic equivalence that we introduced Wednesday. So that's the hope. But is it possible? So this is what we want. And this is what the asymptotic equivalence that I introduced. But if you compare these two, each of these have this order, decay in this order. Therefore, there's big probability that these two may be different from each other. So there's no hope to establish asymptotic equivalence in this case. So what we need is a little bit more sophisticated version of asymptotic equivalence. So this is the generalization of the naive asymptotic equivalence. So we're looking at the same probability. So when normalized by this, the probability that the two objects are far away from each other. If it's not likely, then we say they are asymptotically equivalent. But in this case, we don't blindly consider this event. We actually consider this event conditional on these rare events. So each of these, either one of these, is in this region. So what is this? This is the whole space. These are jumps less than j. So this is basically j or more jumps. And by reducing it, so legitimately j jumps. And the j jump has to be of significant size. So given that, you can actually establish this for these two, and therefore you get the more general notion of asymptotic equivalence. And you can also prove that if you do have this, then the large deviation behavior or M convergence coincide for these two. So we do get the large deviations that we just stated. This argument. Okay, so let me show you an example. So think about the probability of the event that the process hits below B at some point and then end up above A. So something like this. And obviously, the number of jumps required here will be 2, right? You need to go down at least once and then go up at least once. And that's enough. So J will be 2. And therefore, you would expect that it's gonna always happen because flat, lower, going down quickly, and then flat, and then going up quickly, and then staying there. So that's what we actually see in the simulation experiment. As the scaling parameter increases, you do see this pattern. All right, so that was the first topic. Any question?
What is the meaning of Markov modulated?
Oh, so it simply means that it's random. The increments are marked.
Wait, so in this case, this is a autoregressive model.
Right.
This is just autoregressive model. You should maybe use this.
It can be something else, but this is just one example.
Another question is actually it reminds me something classical elements of renewal theory. When you compare this stuff, and I think something like comparison with this random number of cycles and number of size proportion, whatever, it exists already somewhere in the literature. I don't remember exactly, but I can, yeah, it's all there.
Yeah, so please let me know if you find more.
We will check about this. It's a renewal theory, but it's more or less classical.
I see.
What is classical? Renewal theory.
You have IID random variables. It's a typical cycle.
Yes.
And we know that we have this convergence, blah, 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 yes, number of cycles, whatever you would have divided by the length, whatever the length to something, law of large numbers and so on and so on. But you compare, now you want to replace random number of cycles, but it's by its mean. Yeah, what they do,
Yes.
essentially.
Yeah, this is a classical argument, but for the heavy-tailed sample part large deviations, we thought this classical argument should work, and that delayed us with a year because we realized that.
We have to look at it. I'm just.
Just look at read the paper, you'll see. It's very tricky.
Yeah.
So in this case, in those pictures, sort of a single jump would be basically whatever happens within a single cycle, right? So it's not just one large X, it's basically sum within a cycle.
Right.
And a cycle would typically be logarithmic in length.
Sorry.
So if you have a big cycle, right? So cycles are, somewhere, so there is a large value of a size n or something. So then it will end after the logarithmic amount of time, right? And that's why it's sort of, okay, it be sort of squeezed into one.
So this these cycles can be also, so you can also think of cycles from additive dynamics. In such cases, the amount of time you go back will be linear. So
But here is logarithmic.
that's multiplicative.
Can I ask? So the first cycle, say x1 dashed, right? What was that? That was the height of the cycle, or?
Oh, so this is the process
Or the
X.
entire trajectory?
Yeah, so x1 prime will be the area below, like adding up all these over. So R1 adding R1 x size between these times.
And the dynamics of your model, so the fact that this is autoregressive, this x, this comes into the fact you somewhere had, I think, that the tail of this x1 prime was heavy or something like this.
Right,
Yes.
yeah, it's heavy.
Yes.
Yeah, so that's like this is classical way the heavy tails are right.
Yes, of course, it takes a long time. So
What
what?
to prove that? It's not.
Yeah, okay, but I believe it has to prove it. But what I'm wondering is whether this autoregressive dynamics could be replaced by general Markov chain dynamics. And then what is really important for your thing is that is the area under the cycle, how long that takes.
Yeah, exactly. So that
And then the fact that they are autoregressive is not important.
right.
Is
This
that right?
particular form is not important, but as far as you can get the tail asymptotics of the regeneration cycle, and the regeneration cycles are relatively short compared to the size of the cycle.
Yes.
Then you would.
That's the key thing.
The same result holds more or less under Goldie's framework. Charles Goldie has this more general recursion. We have more or less the same assumption. Well,
Yes, okay. Yes. But I mean, the recursion somehow, it seems to me that the properties of these cycles that are important. So you take any chain that has these properties. It doesn't have to be a recursion like that. I mean, It can be
The exact form is
a much more general thing. What is important?
I think the question is how you have proper, you have just, distribution of increment at least X time, the alphabet. How to get a distribution of properties of a cycle?
Yes, of course.
That's the problem.
Of course. But this, I mean, so mine and Tweedy theory sort of starts doing that for quite general things. This is important.
Well, the tail asymptotics of x1 prime is more than half of the paper.
No, I'm not saying it's easy, right? I'm sure your paper is very complicated. This
Yeah.
What do you think about the minus 3D series? So they're not doing large deviation at all, no?
No, they're not doing large deviations, but this Dublin idea, right? To know how long it takes to go away and come back to some small set. This is key, and it's precisely this kind of sort of modulated moments of excursion lengths. This is what happens. This is what plays a role here, right? It's the key thing here. It's not that the thing is also regressive.
Well, I think the minor 3D helps you establish the good properties of the sequence R1, R2, R3. That there exists a good sequence.
Oh, yes, but
That's why you
also
need the minor 3D style theory.
also modulated moments, exactly this. If you take an excursion away from a small set, it's an important quantity for them to know exactly the integral over. And this is precisely what features here.
All right, so any other comments or?
So I think, sorry, to go back to Sergei's comment. Sergei is right. If you are only interested in the one-dimensional asymptotics of Sn at the point 1, then it's probably a much quicker argument based on more classical assumption. But if you want to have the sample part large deviations, you need this generalized asymptotic equivalence stuff.
Right. Okay, that was about multiple content dynamics. So the point is that you need to consider a different topology, and also there are sometimes there are some complications in you may want to use some more refined notion of asymptotic intervals. Okay, so this is a digression that's not very related to machine learning, but because we have talked about so much about conspiracy and catastrophe, and here's Sergey and Dima, I thought I would talk a little bit about the Weibel case as well. So, and Sergey mentioned that I should say heavy tail bite because there are light tail bites as well. So I'm talking about Weibel with alpha between 0 and 1. Okay. All right. So, Weibel sample path large deviation for Weibel random walks or web processes has been already known for a while, and the form of the rate function is this, and so yeah, of course, what this means is roughly that exponential rate is decided by I, and the speed is this thing. But again, this is inherently topological, and what's known has been about L1 topology. So basically, the area of the difference between the two processes. So this is not terribly strong topology. In fact, it's very weak because obviously you can. So this is actually yeah. So before I discuss topology too much, let me first mention what the implication is. So the form of the rate function was the sum of jump sizes raised by power alpha. So here, if this is the path, then the rarity, the rate function evaluated at this path is e to the alpha, e to the alpha, and e to the alpha, somehow. And remember that in regular variation case, the jump sizes, like the rate was decided completely by the number of jumps. Or in case it was double-sided, it still is decided by the cost, but they do not depend on the size of the jump, right? Having this much jump and twice larger jump doesn't change the rate. It's going to show up in those upper and lower bounds, constant in front of it, in front of the rates, but the rate is not going to change. So everything is decided by the number of jumps or some function of the number of jumps. Here, the size actually do matter. We show up here. So this and this, they both cross the boundary, but this one has lower value of rate function, so more likely in terms of the rate. So the most likely reason is exactly because of this. You hit exactly this level, not because you cross the level. So there is some resemblance to the right-tailed dynamics. Right-tailed case, it was this, right? Exactly hitting here. So more larger size leads to different rate, higher rate, like so much less likely, much more rare. So that's a difference. So the form of okay, so yeah, so that's the implication of this, the form of the rate function. What's not great about this result, or what's not enough, what makes it insufficient, is that L1 topology is pretty weak, because if you think about it, these approximate just one jump. So you make the jumps close to enough each other, it will be a very good approximation of this single big jump, a single jump function within L1 topology. So L1 cannot distinguish 3 jumps and 1 jump. Moreover, you can also see that this and this are very close, right? So this one and this one are close to each other in L1 distance. So you cannot tell whether this has crossed or not. Maximum is not continuous with respect to L1 topology. So if you are interested in this kind of probabilities, L1 large deviations with respect to L1 is more or less useless. So our goal was to come up with something that's not L1, that's something with respect to some stronger topology, and ideally J1. So it turns out that J1, it's impossible to establish the regular large deviations principle with respect to J1 topology. So we have its counterexamples. So instead, what we were able to do was to establish so-called extended large deviations principle, which is this. So everything is the same as regular, the classical Varadhan formulation of large deviations principle. The only difference here is that instead of the closure here, we take epsilon fattening and then send epsilon to 0. So this is a looser bound than regular large deviations principle, but still useful enough, for example, to analyze these types of events. And because we cannot actually, we have a counterexample for the J1 full large deviations principle, so regular full large deviations principle. So this is more or less as much as we can get. All right. So, so how useful is this formulation? Again, it's not as useful as the full large deviation principle, but it's pretty useful because we do have contraction principle, although it doesn't. You don't get full contraction principle in the sense that not all the continuous functions, continuous images, lead to those extended large deviations. You need Lipschitz, or well, this is actually not the weakest condition, but at least if you have a Lipschitz condition, Lipschitz continuous mapping, then you do get LFP for its image. All right, so yeah, again, this is showing that how the reinsurance example can be actually addressed by this extended large deviation principle. But then the point here that again, what I would like to emphasize again here is that here now both jump sizes matter and number of jumps matter because it's alpha power. You cannot merge the jumps, right? So if you merge the jumps, then the rate function becomes larger. So you have to divide into three. Wait, no, the other way around. Yeah, if you okay, so sorry about this. Right, so if you can merge them, then it's going to be small. It's going to become smaller, but you do have this condition that you cannot have jump sizes greater than 3. So you have to divide into the number of jumps that gives you less than b, each of them less than b. But if you divide more, then it's going to be larger. So you have to divide only up to minimum number of jumps. So number of jumps matter in that way. But you cannot have arbitrary jump. Like it cannot be b. It has to be as small as possible. And you can also think of these 3 jumps that are of the same size. But if you look at the form of the rate function, it turns out that you have to choose maximum for as much for these 2, and then only the last one you should choose as small as possible. So this means that jump sizes matter, and then they are also asymmetric. You're not going to get the same size same 3 jumps. You have as lopsided jump as possible.
Yes, so you have 2 jumps of some size, and then the last one gets the remainder. Must it happen also at the chronological last jump?
Oh no,
Could
no.
it have been?
So it doesn't have to be, but
Okay.
one of the 3 has to be the smallest. The other 2 has to be the largest. Yeah. All right. Any other questions?
So is life easier when alpha is less than 1/2, say? Can we get something better?
So in terms of the centrifugal large deviation, no difference. I know that it's somewhat curious.
Right, because usually in that case you can get more precise results.
Right. Yeah, but here the rate, like the form of the rate function, and none of those actually matter. Changing when.
But perhaps is getting rid of the logarithms in this case.
Right. It probably has to do with the fact that we have only logarithms. Any other question? All right, so this has allowed to answer some open question that has been there for a while, which is the Q-length aesthetics for the multiple server queue. And this is something that Sergey and Dima must be keenly interested. So, but I would imagine majority of the audience is not as much interested in queuing theory. So let me just quickly mention that you can write the queue length, the probability that queue experiences congestion can be written in terms of a functional that can be bounded by the functional of the random walk, and it leads to the solution of this form. So basically, what to identify what's the most likely reason, you have to optimize this rate function of this form. So the optimization problem that you end up with is in this form, and there are some interesting properties of this solution. In other words, the behavior is quite different from the regularly varying case. And again, because of the asymmetry in both because the size also plays a role here. So yeah, this solves one of the open problems that has been there for a while for the Weibel case, heavy-tailed Weibel case. Okay, let me move on to the rare dense simulation. Again, by the way,
Just before you leave the topic, so are there similar results, like for example, for log normal case, for example?
oh, so yeah, yes. So we do have log normal large deviations. The form is actually same as the regular variation. So only the size, only the number of jumps play the role in terms of the rate.
And it's still logarithmic.
Yeah, right. So we only have logarithmic exponents.
Okay.
All right. Okay. Any other questions? Yeah. So, so the Weibel large deviations, I think it's very interesting because it's like close to the boundary between light tails and heavy tails, and it does show very interesting hybrid dynamics, but it's not too relevant to machine learning because it's still too rare. It's rarer than any polynomial rate, so it quickly becomes very, very rare. So it's probably not what you can easily utilize in controlling some machine learning algorithms. All right, so the next topic is rare event simulation, and again, this is not very relevant, but there was at least one request for more little bit more detail about what I fleshed in the first lecture. So again, so let's think about the simulation like simulation as a computational tool. You want to, for example, you want to understand the probability of coin flip, head in the coin flip, and the easiest way to get a rough estimate is to get run experiments and count the number of frequencies. So flip the coin 100 times, count the number of heads, divide by 100, you get probably somewhere around 4 or 6. And that will be a reasonable estimate of 1/2. If you're interested in rare probability, so that it lands on its edge, not head, not tail, then the probability will be very small. So if you flip only 100 times, chances are you're not going to see this happening anyway. And your answer will have to be 0 based on this computation. But that's not really useful because if if you what you want is to understand what's the risk of certain high stake rare events, then saying 0 is never useful. So you're giving false security. So you'd like to see this happening at least a few times, and to get a rough estimate of the order, let's say. Suppose that it's 1/1,000,000, then you have to flip the coin a few million times to see it happening a few times. So it's much more computationally expensive task. So the way you approach this is one way is to wait until CPU is more powerful and GPU is more massively parallelized. But mathematicians has been taking different approach, which is considering an alternate universe and doing the experiment there, and then recover the true probability from the relationship between the two universes. So what do I mean by alternate universe? Important sampling distribution, an alternative distribution that's not the same as nominal distribution. And then you collect samples from there, and then compute the ratio between the likelihood there and likelihood here. And then report the weighted average, weighted fraction. So you don't just count, you inflate or deflate by the likelihood ratio. This turns out to be the unbiased estimator. And in going back to our context, what this means is to consider random variables. That's 1 if the rare event of our interest happens, or 0 if it doesn't. And obviously these all, so this is scaling, there's scaling parameter n, so the important sampling distribution may depend on those n. And again, this is what your answer is going to be. But this is one of the most popular variance reduction principles. But of course, there's little content here, because what really matters is what's the right choice of Q. So one obvious property that you would expect is that, okay, so rare event simulation is challenging because it's rare. So in Q, you would probably expect that the rare events are shouldn't be as rare. So that will be one principle. But it turns out that these two, the rule of thumb, are these two. So you want to choose Q in such a way that it's as close to the conditional probability as possible. And you also want to make sure that the likelihood ratio does not blow up, because look at the form of your estimator. The likelihood ratio appears here. So if it becomes large from time to time, then you're going to get large variance. So these are the rule of thumb, and the reason why you want to pick a Q close to the conditional distribution as possible is this is actually the ideal one. In other words, if you can pick Q as this one, then you actually get 0 variance estimator. One sample, you get the answer. But that's not realistic, because sampling one sample there means you are able to compute that probability exactly. So that exact choice of this is going to be going to require the answer of the problem. So it's not exactly, this is you cannot choose this. If you can choose this, then you're solving a solved problem. So typically you have to choose something that's close to this based on the knowledge of this. So okay, so you want to choose, that's the principle. How do you know whether it's good or not? So this is a criterion. In other words, if the second moment of your estimator is proportional to the square of the target quantity, then you're good. And this means the number of samples that you have to generate is bounded as the scaling parameter changes. So as the problem becomes more and more challenging, the number of samples you need stays bound. So that's pretty good criteria, like pretty strong criteria. Like you, it's almost as good as you can hope. Or there are cases where the error, relative error is at the deep case, but those are not common. Okay, so this has been considered to be pretty difficult in heavy-tailed context because there has been this very nice light-tailed techniques that allow you to, so based on the large deviation theory and some exponential tilting mechanisms, there has been many light-tailed solutions, but heavy-tailed counterpart has been underdeveloped. But it turns out that there's actually very universal and super simple estimator for in the heavy-tailed context as well. So this is the similar importance sampling distribution. And what is this? This is the nominal original distribution. And this is something that I didn't explain. So I didn't explain what B to the gamma is. But this is mixture of the original distribution and some conditional distribution. So this plays a role of keeping the ratio bounded. And this plays a role that, so this makes this thing, whole thing, close enough to the conditional distribution, the ideal distribution. So what's B gamma? So we would like to choose B gamma in such a way that this and this are close enough to each other. And remember that the regularly varying case, the rate of decay is discrete. So it depends on the number of big jumps. So it's either 1 or 2. There's nothing in between. So everything that falls in 1, they're in the same class and they have some resemblance. So we choose B gamma in such a way that this falls into the same class, but something that's much more tractable. So that is all the paths with exactly J8 jumps, and the sizes are bounded from below by gamma. So what that means is that the J, the minimal number of jumps that have to be added for set A and set B, B gamma, they're equal. So in the same class of variables. So, and also I'm gonna show you this I'm not gonna prove, but I'm gonna show you this is very plausible that you can often choose gamma in such a way that A minus B gamma. So A belongs to A but not in B gamma. That requires many jumps. So twice of J of A. So if you do so, then the second moment actually can be written in this way. And roughly speaking, each of these come from are here because of these, each of these terms, mixtures. And but if you look at the form of these probabilities, they look quite familiar because you know what these what the asymptotics of these are. The large deviation theory tells you that these are these rates. So remember that A and B are the same, so these are the same rates. So it's just square of so it's not written here, but square of this. And then we are assuming that this is greater than the sum of these two, in other words, two of these. Therefore, this is also order of square of the target probability. Therefore, the whole thing is going to be order of square of the target quantity. So that's that was the strong efficiency that we have introduced a few slides ago. So you do get the strong efficiency from this very, very simple mixture importance amplifier. So now we're left with this condition. Why, like how you can choose gamma in such a way that this is greater than this. So, so A was the for example, so we're going to be looking at a particular example where this is something that you are very familiar at this point. So the event that it crosses a level, but with jump sizes less than B. So and B gamma was paths with 3 jumps, but of size greater than gamma. So what's B A minus B gamma? It should cross the level with jump size less than B, but it cannot have jumps that greater than 3. So it has to be at most 2 jumps of size gamma. So these are good, but this one not. If you pick gamma small. So if you pick gamma this much, then it has to be divided into multiple jumps. If you make gamma even smaller, then it should be divided into even more. So that means J of A minus B gamma it can be set arbitrarily large by choosing gamma small enough. So in this case, this will give you small enough, large enough number, which is more greater than twice of J of A, 6. All right. So with this importance sampler, when we apply to the reinference example, this example, and here these are indices of the regular variation. So for different indices of the regular variation, for different scaling parameters, they all stay more or less constant. So more challenging problem instances, you get same efficiency. And if you compare this to naive Monte Carlo, then the naive Monte Carlo has much larger relative error. So this is the log scale, y-axis is log scale. So it's orders of magnitude larger relative error. And this is an example for a stochastic network. So that I didn't explain in detail, but this is the case where you have multiple multiple regular variation index, and so the size of the jobs that arrive to different Q has different regular variation index, and you get the similar result. You have more or less flat relative error for different scales and different configurations of the regular variations. All right, so that was it for today. So let me just mention that, let's quickly mention that what we have, so we have seen what are the catastrophe principles and conspiracy principles. And also we have seen the machineries, like especially heavy-tailed machineries for characterizing the catastrophe principle. And then we also have seen how to lift heavy-tailed large deviations to local stability analysis and then global dynamics analysis. And then we were able to use it for controlling the global dynamics of stochastic gradient descent, so that the SGD can achieve, like, obtains certain property that we want to prove. All right, thank you very much.